Hello everyone, my name is Chilla and I'm delighted to welcome you to our joint webinar hosted by injection molding simulation software provider Moldex3D and CAD/CAM specialist Cimatron. Today we are lucky to have Ken Chang, application engineer of Moldex3D, and from Cimatron we are also joined by David Lindemann, senior application engineer who will present control warping in mold design. Please note that this webinar is being recorded and the copy will be made available after the session. Throughout the presentations, we encourage you to post any question through the chat as we will pause between each session to answer some of the questions. If you like what you see today and would like to be contacted by a Moldex3D or Cimatron representative, please be sure to hit the Contact Us button in the chat window and leave your details. So we have a lot of great things to see. Let's get started. Casey, over to you.
Thank you, Chila. Good morning, good afternoon, everyone. So I am presenting partial of this webinar and why injection molding simulation needed, and then I will explain the workflow of this webinar. So through injection molding simulation, you are able to, before you cut steel, you are able to understanding the gate location, gate size, and you are able to see such as well-aligned air trap flow mark balance. So you are able to understand how the material gonna shrink and warp and also fiber orientation. And for the molders, you also are able to understanding where's the hot spot so you could reduce your cycle time, because the cycle time is also very critical for the molders. And you also are able to use simulation software to understanding the your what material, and then you are able to reduce your mold trial or tooling costs. So in Moldex3D, we use a 3D mesh in order to capture the shear heating, the temperature, fiber orientation, and how the material gonna shear. It also gonna affect your viscosity. Viscosity means how easy or how hard material gonna flow. Also how the affect material shrinkage, and that is why we are able to get more precise results. So before that you cut steel, you are in the earlier design phase, you run simulation, and once you finish your design, then you are going to do the tooling. You also are able to run simulation. So the slides showing you in the earlier you run simulation gonna help you to reduce your cost of your tooling. So this is the workflow of the simulation. You take your CAD model from Cimatron or from the other CAD software, and then you import it into Moldex3D. We generate 3D mesh. And once the mesh is finished, you just select the material, set the process condition. Then you'll be able to understanding like where's hot spot, how the part is going to warp or shrink, and also fiber orientation. So this is just give you an example in order to explain to you. For example, the inner cavity flow faster than the outer, and that is the benefit to understand. Use a simulation software to understand how the temperature distribute during the molding process, and you could see the hot temperature stay in one side, and because the hot temperature gonna make your viscosity lower, and because viscosity is lower, and that is why material gonna flow faster for inner cavity, and it also gonna affect your how the material gonna the fiber orientation and warpage. This is give you an example about the air trap, and then because you know where's the air trap, and then you could put your venting location. And the picture on the right side, it shows you where's the welding line location, and you are able to go back to adjust by your gate location or change the thickness or aiding the flow leader in order to change your flow pattern in order to get flow balance too. And this is give you, like inside Moldex3D, we are able to understand the residual stress induced by flow or induced by thermal. A lot of time, because the residual stress gonna cause your service quality issue or tiger stripe issue. This is give you an example. Original gating is gate from far away from the sink mark. So look at the picture, you could see the sink mark. And then change the gate location closer to the sink mark area. It's gonna help you to use higher packing pressure to pack the part, pack the sink mark area. However, it does not really help you. And then you could change the mold temperature to the lower temperature, because the lower temperature you are going to get frozen layers on the skin. It does help, but you are eventually we still go back to change the part thickness in order to solve sink mark issue. Another one is you are able to run virtual DOE through Moldex3D. So for example, on the left button, there are three control factors: flow time, melt temperature, packing time. And based on those three control factors, you are able to run virtual DOE, and then you could give the initial process condition to your process guy, and then they could, in order to get a minimized warpage. And this is shows you a case study about the warpage validation. So you can see how the part is going to warp, including the roundness. So through roundness, you are able to get it from Moldex3D to understand how the part is going to warp. And then before you color steel, you are able to take export. You could take the exported model that compensates and go back to Cimatron, and that is the key in today's webinar. We are going to present the workflow, how you are able to take the deformed model from Moldex3D and go back to Cimatron to do the warpage compensation. The other molding challenges you are able to simulate is an insert deflection. For example, in the picture left, if the insert is too thin and your gate location is directly, then because the pressure gonna cause your insert bending. Another one will be like conformal cooling. The conformal cooling could due to your part design, and then you could design your conformal cooling, and then you are able to use Moldex3D, understanding how much pressure you will need it in order to push the water through the conformal cooling. Inside Moldex3D, we have more than 9,000 material. We also have material testing lab. We are able to measure the viscosity, PVT, thermal, mechanical property, etc. More advanced is inside Moldex3D, we also have called machine mode. You are able to input the control panel. How do you control your screw? Just like in reality, how you control your screw speed in order to push the material into the mold. This is something you are able to do through Moldex3D. So in our vision is we are going to help the plastic industry, not only from the part design level, but also from tooling for tool makers or for molders, reduce your cycle time, and then trying to understanding how we are able to help you to reduce the warpage and make sure when you are mold the parts, you are able to have a good part quality. So this is the workflow, how we are able to use a compensation method inside Moldex3D. So TD is the target design, which is the original design. And then STD, simulation target design, which is the part going to work. and then we use a compensation target design, CTD, export the model back to Cimatron, and then rerun the simulation. And the SCTD will be after compensation, rerun the simulation. It will be similar to the target design. And this is the workflow. Basically, you follow after couple clicks, you will be able to use a compensation and then export the default model from Moldex3D back to Cimatron. This is in X and Y in Z direction. Same process. You are able to compensate in your X direction, in your Y direction, in your Z direction. And the goal will be the TD will be use this method. You will be able to use a compensation or Kentucky windage. This table shows you could see TD versus SCTD, and you are able to see uniform and non-uniform. And based on this method, you could see TD versus SCTD, they are much closer after user compensation.
Thanks, Casey. Let's pause and take one or two questions from the chat. I do not see any questions coming in right now. So one question that we commonly get, Casey, is what file format does Moldex3D export to Cimatron?
So currently in Moldex3D, we export STL format, which is the universal format. And that is the one of the key in today's webinar is inside Cimatron, you are able to convert the STL format into per solid. So for tool makers or people are using Cimatron, it will be much easier for them to do the design change.
Thank you. And also, usually we get the question that how long it will take to learn Moldex3D.
So with Moldex3D, we will have a live engineer before you launch simulation. We sit with you together, and then we check your model, your mesh, material process before you launch simulation. And usually we do 2 projects. So basically, the learning curve will be 2 projects.
Thank you. One more quick question. Someone is asking if Moldex3D is a Cimatron product.
Moldex3D have a standalone version. If you are going to get a work page result, then you will still need to get a standalone of Moldex3D.
Thank you, Casey. David, this time over to you.
Hey, thank you very much, Chilla. As we go forward with our presentation, we're going to take a close look at both softwares. We'll talk about what's involved in finding the causes for the warpage, how to detect it, how to compensate for it, and then the important thing is when we're done, we're looking for a CAD model that we can use to go ahead with the tool design. So here you're looking at Moldex, and as you can see, Moldex is going to give you the predictive results for all the phases of the injection cycle, the cooling, the filling, packing, all that. So based upon the material, based upon the process conditions, it's going to do the simulation, and it considers everything about the mold, the plastic injection, what type of material again, how you're cooling it. All the factors contribute towards the results that you see in these analyses. Here we're doing a melt front analysis, so you can see how the material is wrapping around those larger columns. I can see, to me, that means there's going to be a weld line. It's a good place to trap air. So right away, I'm finding information that's helping me deduce what's happening with this part. Yeah, other things we see, like in the industry, is people need time to run an analysis like this, but the tool still has to be delivered at the time set. Now here you see the air trap and the weld line conditions. And that results in them having to go ahead, maybe rough burn out their cavity electrodes, using those electrodes, and then come back after the simulation to get the results they want with the warpage. Other factors that we'll look at here include the different pressures that are going to come up, different conditions involving the flow. There's a vast amount of details that you see that it can analyze before we even take it to tooling. Another important thing is to see how the part is cooling. We're going to see any drop, any deviation in the temperatures. Of course, we know the outside of the part, the skin, will cool next to the steel quicker. So internally, we're going to have heat to deal with. That's a form of that's part of the diagnosis of what we look at. And visually, it's nice that you can cut these quick sections, and you'll see a lot of different ways that we can view the information that's being presented to us. So again, thinking about the demands placed on the mold maker or the engineer at the plastics plant, it's important to be able to use these simulations and then understand what the process is going to be. In some cases, with the part coming in brand new, we can run, as Ken said, a design of experiments where we go through and find what is the best process conditions to get the part with the least amount of warpage and go from there. Here we're taking a look at the density. We're taking a look also at how much is involved in the shrinkage. And using the isosurface parameters, we can take a look at areas that have a higher percentage of that shrinkage taking place. So we can see it's not uniform, of course, because of the thicker wall conditions. And that helps us to understand how that part will warp. All right. Another situation that people run into a lot is they've gone ahead and cut the cavity in core steel. Now they got the part visually, you can see it's warped even after it's been sitting out for a day or two. So they take their measurements, and now they find out that they're going to have to scrap their cavity and core. How much easier it could be on them, to be able to do the simulation first and understand the things that are taking place here. So as I go through some of these things on the left hand, you can see, you know, Moldex gives you a good way of looking at the part so that you can understand the color ranges and values, that you can also see, how much of a percentage of the part is within those particular ranges. All right, looking at cooling, this is a very important factor. We want to see uniform cooling. So I see a lot of blues, and I see some of the color just starting to get into that green range, and on the right, I can kind of see the maximum, the minimum as I scale through, using this isometric surfacing to visualize it. So that's all well and good, and that helps me. But another factor is to see how much of this blue and green are involved in the part. So right here, when I took a look at the analysis, the report, I can see it looks good, right? There's at the bottom in the cooler sections, I've got the majority of the part, but I still see a range of something like up to 25, 30 degrees. So if I can fine tune that, I'm going to get rid of the warpage. Clearly it's in the center where it's originating from. So people using this, we've seen them, create conformal cooling lines to wiggle their way in through that type of geometry. And then as they run the analysis, they see areas that aren't dark blue, and they'll just start nudging those conformal lines, push it in a little further, rerun the analysis, push it in again until they get the constant dark blue that they're looking for. So throughout the process, we can refer to these simulations to help us understand, what we're doing that's affecting the part quality, making it better. All that now having been looked at, we can go into the warpage. So what we're going to do is calculate the warpage model, and we'll see how that warpage is affecting it. And again, you can see clearly in the center, it's pulling in. Now to visualize that, we can create the quick little movie clip so we can see the in and out of it. You might see it on the screen here, kind of expanding and contracting. Perhaps I want to see it more dramatically. We can exaggerate it. So I'm going to up that factor, and I can really see it towing in. And, that's going to help me understand that there's a lot going on in this part as far as what the warpage is causing. So more than likely, I would have a lot of work to do on the CAD side. in order to get the mold developed. From here, we'll export the STL. So that's going to come out of the system as we choose, either without the compensation or with, and then also the shrink factor. The part's gone through simulation. The shrinkage will have affected the model. We can take that STL, and at this point, we want to take that into Cimatron, and then we'll begin working with it. So you see the handshake goes from the simulation model into Cimatron, and now that STL is going to be what we work from. But again, in the end of this, what we want is a workable CAD model so that we can go ahead with an easier tool design.
Thank you. Let's pause and take one or two questions from the chat. I see one asking, will Moldex3D suggest gate locations and size? Casey, I think this is still for you.
Yes. So basically, we do have function could give you the where are the best gate location. However, some of area you probably due to service quality, you probably don't want to get in those area. So eventually, you still need to do a quick flow simulation in order to understanding where's the best gate location. So you are able to use the simulation results to discuss with your customers or modders to see if you could choose that area for the gate location.
Thank you, Casey. And there is one commonly asked question. What is the typical time that it takes to get the warp-pitched model in Moldex3D?
So in order to run like cooling flow pack cool warpage, usually one of the model like few hours, and you could run couple iterations in one day. So if let's say give like a few hours to get a warpage from Moldex3D, and then just few click, you could export the STL model to Cimatron. So a couple hours.
Thank you. I will take one more quick. Cimatron exports which file types for tooling from the windage part?
If we're to take the model file and hand that over to Moldex, typically we use STEP. That's the best way to get in, but there are several translators that we have to translate out with, and then also that Moldex has that they can read in. So your typical ones are there, and STEP is the one pretty much everyone uses.
Thank you, David. We will answer more questions after the webinar. We can move on.
Okay, thank you, Chilla. Thank you for those questions. So a little bit about Cimatron. Cimatron is a software, CAD/CAM software that's specifically for the tooling industry. So for molds, for dies, for cutting, CNC work, for 5-axis programming, electrode work, Cimatron is totally invested in working on that type of tooling and other forms of tooling that are similar. So that means as a mold designer, when he goes to the software and he starts working with the different functions, the CAD functions, he's not wrapped up in the functionality name itself, but he sees things that relate to his industry. If he wants to build a water line, he goes to a part of the menu that says water lines, and then it systematically goes through the thought process. So the way a mold designer would go through the work are the steps that the software presents to him as he makes these decisions. So you can understand then why Cimatron is a leading software in terms of getting tool delivery done, or making changes, because it's highly geared toward those industries. So as we talk further about part warpage in a mold, KC had earlier mentioned about Kentucky windage, and perhaps you've heard that term. I hear it a lot here in the States, and it comes from marksmanship. So the idea is if you've got a moving target, you can't take dead aim at it, you'll miss. The target will have passed that point before the bullet even gets there. So you aim ahead of it and you're guessing how much you need to go ahead in order to hit that target. That's kind of what Kentucky windage is. How much are we guessing that part's going to warp away from where it should be so that we can hit it in the right spot? Well, so many things affect that. One's just the part design, the different thicknesses of the part, the fiber orientation, and how the plastic flows in, left and right, front, back. It can have a flow in a transverse direction to it. The part shrinkage. As we looked at some of those simulations, we can see not every area of the part necessarily shrinks the same way. Also, the temperature is a huge factor. If our water lines are irregular or ineffective, we could have a part cool before another area of that part cools, and that will definitely cause warpage. So a lot of time and thought has to go into this. Do we redesign the water lines and take on maybe more like a conformal water line approach, where we can take it through some tougher geometries and kind of snake it around the part in order to get the cooling that we need? For most, it remains an educated guess. They're going to have to go ahead, cut the cavity and core the way they think it's going to turn out. After they mold the part, they check it, get points on it, and now they have to go back and adjust the cavity steels. More than likely, that means they have to scrap their first pair of inserts. So you can see where it takes time. And if we had the ability to actually use the warpage and compensate for it at the beginning, that could save us a lot of time and expense. So the solution we're looking for here is to have the software capture all that. We know the process. It's going to reflect in the tool, the way we tool for that warpage. And at the end, we need to have a workable CAD model, not just an STL, but that CAD model so that we can do our mold splits, pull our inserts, and do all the design work. All right, so let's get into Cimatron. Where our story left off, we had created the STL. Now I'm going to bring the STL into Cimatron, and already on the screen I have the CAD file. So that was imported in previously. Also, the CAD file is set up so that I can work with it as I would a tooling condition. So what I want to do is to work with the STL, but make sure that my numbers reflect what I'm going to see with the tool model, which would include, expansion, all those important things for the material. Okay, first thing is to look at the STL and see what I've got here. So I'm doing a draft angle analysis on it. And what you see based on the range of colors and values is anything in red in that pole direction, which is the pink arrow, that's undercut. So along these bosses that are sticking out the bottom, I've got about 2 degrees of undercut. Or I may see some undercut too, depending upon the pole direction along the side of the part. Well, that's going to be typical because if I've warped it, I'm bending and bowing, and some areas that were near straight, are going to go past vertical. So I will have to deal with that in order to have a moldable part. So again, here, let's look at the two, and I can see they don't quite line up even. I know that one is smaller. The STL will be smaller because the simulation has accounted for the shrinkage. So from here, I want to work with the two and get them on, I guess, the same plane, same location as what we're working with. So I'm just going to quickly at this point, we'll snap a couple of dimensions on here, and then I can compare what it looks like. So here you're looking at some PMI dimensions. We won't, go verse by verse through everything that's here in Cimatron, but hopefully enough that you can see how we handle this process of warpage. So there's my first PMI on the STL file, and I'll find exactly the same other dimension here on the CAD file. And I've got something to compare it to. Looks like I've got that reversed. I did the CAD file first. With these two dimensions, though, I just simply divide one by the other, and that gives me the equation to know how much the shrinkage, that shrink factor, is involved. And from there, I can now expand the STL, scale it, so that it matches, what's happening with the part. To get super specific, we can do it differently in the X and Y direction, Z direction as well. All right, so now I'm fairly confident that those parts are much more even in size, minus our shrink factor. From here, there's another concern with the warpage. The part is bowed, so how do I line it up? Do I start at one end and try to line that up and then hope it looks pretty good at the other end? Am I trying to work from the center? This tool allows me to align up the original file to the STL, and it looks at the geometric center of the part. So mathematically, I'm analyzing overall width, length, height, and trying to find the medium, the center of it. And just comparing the lighter colored STL file to the darker colored CAD file, I can, clearly see the deviation now. Where it bleeds together is close, but boy, you can sure see it bowing here on the end. You can see that those posts are bent out, and the warpage is kind of pulling the edges in towards center. So what was once straight isn't looking straight anymore. Out here on the ends, it looks like that STL file is twisted. So there's a bit involved here. So imagine, call it the old days, right, where a designer would have to now remodel the CAD file to match this, or in reality, do it in the opposite direction to get the compensation. That is a ton of work. Some designers will talk about the hours, the days of preparation that goes into getting the model ready for tooling once they got the STL. So, we appreciate that any tool that can help us to deal with this and save time is a huge, it's just a huge good thing to have. All right, so I'm cutting cross sections here, and I want to take a look at how much I see things that aren't near vertical, or has it lined up right. It looks good to me from here, so I'd be pretty happy to work with it. And now go ahead and do the work on the compensation. So it's important to know where we're at and make sure that we're fully understanding what we're up against here. Okay, so to begin the method of compensating, I'll first of all create my own point cloud. So I'm going to spray the points across the CAD file, and where those points touch, that's going to be my reference. I can control the tolerance, of course, the amount of points I want to use by how far the distance apart will be. Do I want those to go up the vertical wall? Yes, I do, because I want to capture whatever draft angle is there. So that will become a huge factor. Once we've gone and calculated the points, I take a close look at the dots, the points, and if, as I move the part around, or turn off the part, if I see enough geometry in the points to recognize it well, to see that the features are there, now I feel like I've got a decent enough point spread to work with and capture all the detail. I don't want a whole lot if I don't need them, but if I can get a good spread, it's better to have more than not enough. All right, so let's take those points now, and we're going to work with the STL. We're basically going to snap them down to the STL surfaces and compare the distances. And the way I like to do it is to keep a separate file. So this is a CSV file, or comma delineated kind of file. And I do that because I may have other iterations of this. I may go back to the simulation, tweak the water, run it again. Now I want to compare the two. Well, I've got the simulation with the points set for as it was initially, say out of the box, or how I've maybe tweaked the process, or how I've tweaked the design. So I can keep those different versions available for me at any time. Let's go ahead and save the file now. And that's what we're going to work with. That's captured the intelligence that we need. All right, so there we can turn off our STL. Here I'm bringing the CAD file back up. That way we can reference them. And I want to now run this analysis. Okay, so what's involved? Well, what part am I working with? And then how do I want to control orientation? So it's going to factor in the Z vector direction, and this is huge because all those vertical, near vertical walls are going to be handled understanding the pull direction is in Z. So that is going to reflect on those undercuts we talked about earlier. All right, now I'm going to bring my point file in, the one we just created. You see there's several points to work with, a few thousand or so. That number can get pretty high when you're dealing with the complicated part. All right, as I zoomed up, the light little white lines, those reflect the vector of how the point would move, comparing the two. So I've captured the distance in between. Now my choice is, do I want to run 100% of that deviation to get a full compensation. Do I want to run 120%? Maybe I want to go 80% and stay a little steel safe. It's up to me. So again, you can have a couple different versions of this. Do I want to push the point in the same direction? No, what we want is to do the opposite direction. Okay, so while the part may bow in or up, now we want to compensate by having it bow down or out. Okay, so we're going to get the opposite effect of the STL, and that's the information we're looking for. So think of all the little measurements you would have to take to find how much it's varied in warpage from the original to the STL file, and now reverse all those, and now model the part based on that. Again, that's a huge amount of work that has confronted the industry here. So we'll go ahead and run the calculation, and this gives you an idea, how long it takes. It's for as much work as it does, it's not really taking a terrible amount of time. So let's zoom up on the end and look at this. There you've got the original STL. All right, so you've got the one that has the warpage, and now the darker orange, that's our compensated model. So you can see just how much it's pushed it in the opposite direction. That's what we would tool our mold to. Okay. Other things will go into that. Before we go forward though, let's rerun this. And this time I want to keep the original. So we're going to have all three versions. And this is a way for me to double check just to make sure I didn't flip the arrow the wrong way, or instead of clicking on opposite, I clicked on same direction. Simple thing like that. All right. So when we rerun it, we now see the three parts all together. The light orange, that is the STL file. So let's turn that off. I'll simply hide it. Then the next layer is the original CAD file. Finally, now we have the compensated CAD file. That's what we were looking for. That's the one we want. Okay. Now, of course, we've got our due diligence to do. And we always say check, double check, and then recheck. Let's make sure we've done everything. Make sure we haven't skipped a little problem area. There's still some things to think about when working with this part. First thing is I want to double check the draft conditions. I know the STL file had undercuts, but here when I look at this compensated part, again, based on the color ranges, the values I type in, I'm seeing as I move the tooltip around the different features that it's holding a positive direction. All right, so I've got a good draft angle. Even down here on the side, I've got half a degree of draft working for me. And the direction it's reading it in is going to that direction of that pink arrow that you see. So if I flip it here and take a look at the coarse side, those bosses were definitely undercut. Had a good 2 degrees on them. Now I see the draft's in the right direction. It fixed it for me because it knows that Z direction of pull. That's huge. That's going to save me hours of work. And now with that, let's go ahead and take another look at something. While I'm warping and twisting this part in a simulation, what's happening to the wall thickness? That's also a big deal because I don't want to thin it. I definitely don't want it to bunch up in an area either. That's just going to create another issue for me. So let's do an analysis now of wall thickness. So what this tool will do is wherever I pick on the part, it imagines a ball that would fit inside all those surfaces. So it's going to tangentially touch every nearby surface within that range. So see the cursor as I move it along the part? Those wall thicknesses are pretty consistent. Then other areas that were thicker, areas that I knew were thicker ahead of time actually, are still that same thickness as well. There on the left, you kind of can see, underneath the values here, this pull down I got, you can kind of see the max thickness. So I put a big ball in there. Maybe there's an area I want to touch up a bit and change the color so that it stands up higher here. Now we can see these thicker areas. This might be something I need to talk to the customer about. Can we thin that? And maybe that'll reduce some warpage for us. So from here, we can take this and save it as a PDF, and then we can send that on, to the customer to talk to him. All right. So looking at maybe a little more detail here. The ranges of colors are nice, but again, just a simple click and there it's putting in those spheres wherever I click. Right? So I can highlight key areas of importance. Another way of taking a measurement is what's called a ray analysis. So wherever I click on that face, it's going to look normal and shoot across the part. So if it finds the opposing side, that could be the wall thickness. In this case, most cases it is. If I click on the end and all the way to the other end, and I've got the overall length. So I'm looking at areas in particular that I know are going to give me a measurement for the wall thickness. Right? And there I've got some important data now that I can present to the customer. Here is another great way to understand what is happening with the wall thickness. Am I consistent from front to back, from side to side? Well, we can cut this cross section. Along the cross section, I'm seeing the warpage. I can see that the bottom's not perfectly flat. Okay, so definitely it's there. But at any position I see it's important, I can go ahead and snap that and then, take a look at it in greater detail. So for instance, let's go side to side here. We'll look along the whole length. That would probably be the best indicator for me if there's any areas where the wall thickness has been changed. All right, so we get into this key area here. Now we'll calculate that, and it gives me those color ranges again, but here just on the cross section. All right, so I can see that the general thickness is in that light blue, and it's just barely touching on the dark blue, which means it's holding pretty consistent all the way through. Of course, where there's a wall intersection, yeah, that's thicker. Okay, that makes sense. But overall, I would say that this is telling me that I've held a consistent wall thickness. All right. So again, let's take that. We can send it to a PDF. And now that information is stuff that we can share with our customer. Okay, so far, pretty straightforward. I haven't had to touch the model too much. All right. There are areas, though, that as I look at it, I might want to make adjustments. So I'm going to take the original CAD file and we turn it this yellowy color here. So I can see that versus the file that's got the compensation in it. Okay. Maybe there's areas in the geometry I need to adjust. One of the things I need to look at a hole location. I want my holes to still be in the pull direction. So am I still on location where maybe existing core pins already are? Here I could see with the colors bleeding through between the two that yes, it's held those hole locations. So the warpage hasn't affected it that drastically. Do I want to keep my rounds perfectly round? I would check for roundness. Exactly. Especially if it's something that's like in a side pull. I would take a close look at maybe adjusting that to a standard round situation. Okay. Well, how do I make these little tweaks? Here, dragging through, I'm still looking at the wall thicknesses, and you can see like the near verticals, everything drafts out nicely. So the new draft I have is very comparable to the original draft. So I'd be very happy with that. Let's say down here in the corner, it's warped considerably, but I need to maintain something right along parting. Right, that's something that the customer insists I hold for whatever his design conditions are. And I could see it's slightly out here. All right, so even after having gone through the big version of the software where I point all these points, I can now go back or just simply grab a point on the part and now snap it back to the original. So maybe along this back wall here, I'll say at this point, snap it up to that point. That's straightforward. And I'll see it basically bring that whole part into that position. So it's just kind of just nudging it for me to line those two up. All right. So that's something that's just there with this in software. So if you have a simple change, it's pretty straightforward to go ahead and just snap a part out like that, and you'll see it bow. Like maybe the part on the one side bows in, so you have to compensate. Say it bows in 1.5 millimeters, you have to compensate by bowing it out 1.5 millimeters. That is very possible just with this one click here, this one function. All right, we knew that the bosses down on the other side, though, the core side, were definitely out. And now looking at them, I might wonder, are they straight? I probably want to touch that up a bit. Also, the location is that looks like they've stepped out a bit. All right. So if I've already tooled this, and I want to replace my cavity insert here, I still would want to measure up to right where that ejector pin location is. So let's say I put an ejector pin at the bottom of that boss. That's what we want to address. Here in this measurement tool, I'm looking at areas where in the blue it's gotten bigger, whereas in the purple it's gotten a little smaller. So I'm seeing the motion, comparing one part to the next, and I can get it and specifically measure exactly how far away one is from the other. All right, so it's a few thousandths. We're going to take that now and push it back to the original, so that it lines up to that position where I know that ejector pin is. And this is something we call direct modeling. So it's another tool within this toolbox we have in Cimatron to deal with all this type of geometry. So I'm picking the component, and it's up to me. Do I want to just push one side of it? Maybe I want to grab the whole feature. In this case, it makes sense to do just that. So I might box pick or window pick, put a lasso around it. You know, so any way that I see fit that's going to grab the geometry for me. And now let's just push it to the side. So I can move it linearly, I can move it radially, offset it, make it bigger, smaller, all that you would typically think of when you're doing direct modeling. Right. So now I'm looking at it, and clearly it's been pushed back. I can see, more of that original part now, the original color. So back we go. Let's do our measurement. Well, got ahead of myself. Let's go ahead first and do the other side. So we'll push that over just like we did before. Same distance. Okay, done. A lot easier than, moving it manually than retrimming. Okay. All right, let's go ahead now and take a look at those distances. So from one part, the new part, to the old part. And then again, looking at the color range, which I know are going to be purple and blue, I can see a lot more bleed through between the colors. So it's telling me now when I go to measure that I'm just about right on it. All right, so that's done it for me effectively. Now I've got that back to where I need it to be. So like we said, there's a lot that goes into dealing with warpage, and no two parts are the same, and there are different causes for the different warp conditions we measure, right? We like to know what those causes are so that we know how to attack the situation. But here, hopefully, you've seen some tools that greatly take down that workload. That we can look at the draft angle conditions and we can deal with those. Also, we can deal with all these different positions, the way the part may warp, and we can capture that, reverse that, now save that into a CAD file and make little tweaks along the way if we desire. So there it is. You've got the handoff from Moldex to Cimatron, and now going forward, let's look at the process. Here we see one more due diligence. Okay, we've got the part corrected. Let's send it back to Moldex, run it one more time with the same process conditions, and let's see if it warps to the correct part, that initial design part that we want to see. Okay, well, thank you very much. That gets us through our material today. Let's give our attention back to Chilla to see if we have any questions.
Thank you, David. Let's take one or two questions from the chat. Someone is asking, could you import a CT scan model of the actual wrap part to Cimatron to do the compensation?
A CT scan. I will have to check on that. I know that we take a lot of things from CMM machines. We can directly import some of those. Yeah, let me double check on that. We can get back to you on that.
Okay, there is another one. What about making circular holes into X-shaped holes with anisotropic compensation?
You want to take a circular hole into an X-shaped hole.
Egg-shaped hole.
Egg-shaped hole. Oh, I understand now. Why don't we look at that maybe later? Maybe that's a good one we can do in the session. See if something on the part reflects the condition we're talking about and see what we can do there.
Okay. Well, thank you. Any other questions can be asked and addressed in the sessions after the webinar. Let me close by thanking our presenters and thank you for joining us today. If you would like to discuss any other topic or would like to arrange a company meeting, please hit the Contact Us button and we will be in touch shortly. At this time, I'd like to direct you to our session area where we will have live demonstrations from both Moldex3D and Cimatron. Our presenters will be in their respective sessions to further answer any questions you may have and to give short demos of what you have seen in today's webinar. We also encourage you to visit our expo area for more information about both Cimatron and Moldex3D. The expo area provides downloadable PDFs, brochures, and videos that dive deeper into what you have seen today. You can find both the session and the expo area in the icons of the left-hand side of your screen. Again, we thank you for joining today's webinar and hope that you have a great day. Thank you.